Good morning, everyone. I'm Yunlei Zhao from Fudan University, Shanghai, China. I'm going to talk about identity-based authenticated encryption with identity confidentiality. High encryption is a new cryptographic primitive introduced at CCS 2016. Which integrates public key encryption, entity authentication, and identity concealment into a monolithic primitive. It can be viewed as privacy-enhanced encryption. Identity privacy is a fundamental privacy concern, which is mandated by many cryptographic standards and enforced by laws. In this work, we present the first identity-based high encryption, referred to as IB high encryption, IBHC for short. It is almost as efficient as CCA secure Bernard Franklin identity-based encryption, but offering entity authentication and ID privacy for free. It's more efficient than the state-of-the-art of identity-based encryption in the IEEE P1363.3 standard, and additionally offering ID privacy, receiver deniability, and access security simultaneously. It's significantly more efficient than the IBC standards used in 5th-generation mission-critical communication. And also, unlike a traditional IBC, IBHC does not have the traditional master public key, which is more efficient and eases the compatibility with existing IBC systems. Now we introduce the definition and security model of IB high encryption. IB high encryption scheme consists of 4 algorithms. On input of the security parameter, the setup algorithm outputs the system parameter and the master secret key. Note that setup does not necessarily output the traditional master public key. On system parameter, master secret key, and the ID of a party, the key generation algorithm outputs the secret key for that party. On system parameter, the secret key and the identity of the sender, and also the receiver's identity, and the message M, and some associated data H. The IB high crypted algorithm outputs the ciphertext C, or a special symbol denoting about. On system parameter, the secret key and the identity of the receiver and the ciphertext C, the IB high crypted algorithm outputs the identity of the sender and also the message M, or a special symbol denoting about. In the security model, we assume a very general setting and consequently more powerful adversaries. We allow IB high crypted message to oneself, that is, the sender and the receiver can be the same party. We allow adaptive party corruption, that is, the corrupted parties are not set on-set, but made adaptively during the attack. We also allow more exposure of some intermediate yet critical secrecy or states. We have 2 security goals The goal of outside enforceability is to force a valid IB high crypto test on behalf of an uncorrupted sender to an uncorrupted receiver, where the sender and the receiver may be the same party. The goal of inside confidentiality is to break the confidentiality of the message or the privacy of the sender's identity for any IB high crypto test from any even corrupted sender to any uncorrupted receiver, even if the attacker is allowed to corrupt the sender and to expose the intermediate randomness used for generating other ciphertexts. Now, we give the construction of IB high encryption and discuss its features. Let ink and DEC be an authenticated encryption with associated data H. E is a bilinear pairing of type 1. H is a mapping to point hash. KDF is a key derivation function. For each user, each secret key is the hash of its identity to the power of small s. Small s is the master secret key. Note that here we do not have the traditional master public key. To IB high crypto a message, the sender chooses the exponent small x uniformly at random from ZQ star. It computes the big X as the hash of its identity to the power of small x. Then the sender derives the setting key K1 from the primary secret PS, big X, and the identity of the receiver. And then the sender uses K1 and running the AED scheme to encrypt its identity, the message M, and the exponent small x to form the ciphertext CAE. And finally, the sender sends CAE big X together with the associated data H to the receiver. After receiving them, the receiver computes PS as the pairing of big X and its own secret key, and then derives K1 from PS and big X and its identity. And then the receiver uses K1 to decrypt the ciphertext CAE to get the sender's identity, the message M, and the exponent small x. The receiver accepts the ciphertext if the following holds. It checks whether the exponent x in the Q star and the big X equals the hash of the sender's identity to the power of the exponent small x. This is the protocol construction. This protocol enjoys some interesting features. Firstly, it enjoys forward ID privacy in the sense that players' identity privacy is preserved even when its static secret key is compromised. It enjoys X security, that is, the leakage of the exponent X does not expose the sender's static secret key or the primary secret PS. It also enjoys receiver deniability in the sense that the session transcript can be simulated from the public parameters and the secret key of the only receiver. We prove that this protocol is secure in a random oracle model and the associated encryption security and the gap SBDH assumption. We also show that the gap SBDH assumption is in turn equivalent to the traditional gap BDH assumption. That is, the BDH problem is hard even if given Oracle access to a DB-DH Oracle. Finally, we compare our construction with several important IBC standards. In comparison with the CCA secure Bernard-Franklin identity-based encryption, our IB high encryption scheme has much simpler, much shorter public parameters, and also has a much simpler setup states. Specifically, our scheme does not need to generate the traditional master public key. The key generation algorithm for IB high encryption and that for Bernard-Franklin IBE are the same. The computational complexity of the sender and also the receiver are roughly the same. In this sense, the entity authentication and the identity privacy properties offered by IB high encryption are gotten almost for free. The identity-based sign encryption standard in IEEE P 1363.3 is based on bilinear pairing of type 2 and can be viewed as the state of the art of identity-based sign encryption. In comparison, our IB high encryption scheme has a much shorter system parameter and has a much more efficient setup stage, as well as much more efficient key generation stage. And the total computational complexity of sender and the receiver is also much more efficient than that of the IEEE P 1363.3 standard. In addition, our scheme enjoys forward ID privacy, X security, and receiver deniability, while no one is offered by the IEEE standard. Also, the Identity-based cycryption standard is based on kill BDHIP assumption, and our scheme is based on relatively more standard gap BDH assumption. Finally, thank you, all of you,